What I'd like to tell you about is the life history of drops from its birth to its death. And this is, I want this to be somehow, this idea of the biography of a drop is somehow the glue that's going to bring in certain different aspects of fluid mechanics that I want to talk about today. So the main thing I'm going to try to show you is that there are surprises throughout fluid mechanics, and you'll see so many surprises. And that means that there's really quite deep science going on there. And we can see this in a number of different cases through just this life history of a drop. And so I'm going to be focusing on just those transitions. So Plato had said about philosophy that philosophy begins in wonder. And I certainly think that that's also applicable to physics and certainly fluid mechanics. So if you just watch the way fluids behave, I mean, at some point you just have to give up and just be in wonder. I mean, because they're beautiful, they're aesthetic, they're complicated, and reproducible. It's everything that you could ask. And fluids are also a wonderful thing because they are a test bed for so many different types of questions in physics. And some of the most difficult and important questions today, I think, have roots right here in fluid mechanics. So, for example, it was already mentioned that I like disorder, and yes, I think disorder is a very important thing because, we learn, when we first start taking any physics courses, we learn about perfectly ordered things. And then I go out of the physics class and I look around and I don't see anything that's ordered. And so that means unless we have a way of translating the ideas that we understood for perfectly ordered crystals into the disarray of the world around us, physics doesn't have that much to say. And I do think physics has a lot to say, but you have to do that through really specifically trying to understand certain aspects of disorder. Another thing that fluids have is that they're very nonlinear. And so, again, in physics, we're taught very much about how to learn and treat linear things. So, what do I mean by linear? So if you walk down the street and you bump into someone, you get a certain reaction, and that's a linear reaction. But if you bump into them a little harder, they turn around and hit you. That's a nonlinear reaction, right? I mean, and that's also part of our world. And so, understanding how physics should begin to treat nonlinear phenomena, I think, is a very important aspect of modern science. Perhaps the one that I'm most excited about in all of this is that, again, physics has taught us a lot about treating equilibrium systems. And so, if you give me a box and fill it with gas, I can probably tell you more than you would ever care to know about the properties of that gas. Why? Because it's an equilibrium. It has gotten to as dull a state as it possibly can get, and I can tell you, bore you to death with all the things that we can learn how to do about that. But then you look around you, and the world is not in equilibrium. The weather outside is not an equilibrium phenomena. And so all of the interesting things that we have to deal with this fact that we're not in equilibrium. Another example of not being in equilibrium is, well, you're not in equilibrium. If you were in equilibrium, you'd be dead. Not only would you be dead, you'd be homogeneous, and it'd be a very dull kind of death. I mean, it would be just not worth dying for. I mean, one of the things that this ideas of going far from equilibrium is, this is a way of getting you a little bit closer to the ideas of biology, where biology is all geared to trying to keep us from this bland equilibrium. So this is one of the test beds of various basic issues. Other things that it does is its flow. Liquids can flow, but they can also freeze. And so you have this transition between a flowing state and rigidity. And you can go all the way from a gas all the way to a glass. I mean, so all of this stuff spans what liquids are able to do for you. So it's starting from liquids that you can begin to think about aspects such as the glass transition, how things freeze into a disordered state, jamming. All of these issues stem from fluids. But the other part I just want to point out is that surprises abound. And it's really fluids, among other things, make up the texture of our world. And so what do I mean by that? Well, there are various patterns. And so let me see if I can show you a pattern that is perhaps surprising to you. So I have here two plastic discs. Okay, so they're just plastic discs. And if it survived going through customs, I have some paint here. And so what I'm going to do is I'm going to put a little dot of paint in the center of one of those discs. Okay? Now, what I'm now going to do is do something which I hope you will find rather dull. That is, I'm just going to squeeze this paint down with the other disc. And you see it's just going out in a very smooth, dull circle. Okay? So what was so interesting about that? Well, that part was not so interesting. But what happens when I take it apart? Okay. So that's what you get when you take it apart. It was totally unstable. You have a new unstable type of pattern formation. It has a kinship to so many things that you see around you. The trees that you see in winter with all the bare branches. You look at the delta of a big river and you see how that branches up into smaller and smaller rivulets. All of these things have some aspect similar to this, what's called viscous fingering phenomena that I could just demonstrate for you right here, and which is a topic that's something we continue to study in the lab today. So I'm going to turn this off now. This stuff is still wet, so I'm not going to pass it around. But by the end of the lecture, it should be dry enough for some lucky person to take it home. Okay, so that's the. Okay, so that is what I mean by some of the surprises that come along. Okay, so I told you I was going to now try to tell the story in terms of the biography of a liquid drop. And what am I interested in here is, so this is one example. So this is a drop of water that's falling. And what's happening at this instant is this drop of water is just on the verge of breaking into two pieces. So here's the drop down below here. Here's the rest of the liquid hanging from the top surface. And a moment later, this thing will be disconnected right at that point. Okay? What's happening at that point? Well, this thing was singly connected now. A moment later, it'll be two pieces, so there'll be a change of topology, for example. But associated with that change in topology, there's another thing that's going on, which is right at this point, if you look at this cylinder of liquid that's coming down, it's a cylinder, it's a circle, and right as you're getting closer and closer to this point of breaking up, that circle is getting smaller and smaller and smaller and smaller. Indeed, for it to break apart, that circle has to shrink to zero radius, right? If it's not zero radius, it's still connected. So it has to shrink all the way to zero radius. Well, one thing we know about fluids, I'll just state this fact now, is that we know that there's a pressure change between the inside of a fluid and the outside of a fluid, and this is just proportional to the curvature of the liquid at that point, which is 1 over the radius. So if that radius is going to 0, that curvature is getting infinitely large. 1 over that 0 goes to very, very large. So that curvature times this quantity we know about fluids, which is called the surface tension. Surface tension is just what tries to take a fluid and make a sphere out of it to get the smallest surface area. So what that's saying is just at the point of breakup, where this transition is happening, I'm also getting an infinity coming into my problem. It's get infinitely forced at that point because I have this divergence in that pressure difference between the inside and the outside. That's as much force as it can possibly happening right at that point to try and keep this thing breaking apart. So something is happening, and so how do I try to study this? Well, I put it on a computer, and it's not that I don't know the equations. I know the equations all right, so we put them on the computer, and you run them, and you get it at some point, and you realize, well, that's not far enough, so I want to go farther. I want to get closer to the point of breakup. So I work harder, and I get a little bit closer, and that's still not close enough. So I work even harder, and I get a little bit closer. I have to work harder each time because this thing is getting smaller, and this is remaining the same size, so I have to resolve all those length scales as I do this. I work harder to get closer, harder, closer, and it's Zeno's paradox all over again. No matter how hard I work, I can only approach that singularity. I can't get to the other side of that singularity. And so this is the thing that we're stuck with. But then you look out the window on a rainy day and you see a drop hanging from the eaves of your house, and it just falls. I mean, it's not sitting there trying to figure out, well, how do I do this? It just falls. So the fact that it falls and has no trouble falling, and we have to sit here and ponder what do we do, means that there's something about the physics that we don't understand. And so that's the issue that I want to bring apart. So this is what you get for just this ordinary drop on a tabletop. But you see the same kind of phenomena at all different scales. So, well, the lighting here isn't so great, but you probably have seen this image before. It's probably the most famous image that came from the Hubble Space Telescope. And so these are what are called the pillars of creation. These are star-forming regions in the Eagle Nebula. And what's going to happen here are these big clouds of gas are going to coalesce into stars. And in order to do that, this connected thing has got to break up into pieces. And here again, we have that same kind of problem again. That is, how does something that's singly connected break up into more than one area? You can go, that's at the larger scale, you can go down to bacteria colonies, and you see bacteria colonies, the bacteria communicate with each other by sending out pheromones or whatever well, that's not what bacteria do, but whatever bacteria do, they have chemicals that interact with one another. And so you can get these long lines of the bacteria, and these long lines then break apart into sublines. Again, that's the same problem. How does this one long line break up into more than one? Go down even farther, and you go to nuclear physics. And so you have Niels Bohr told us the nucleus is a liquid drop. Well, if you have the liquid drop model and the nucleus fissions, that's again the same kind of thing, just with fewer particles in this case. So we've gone through from the celestial scale at the star formation level all the way down to nuclear fission, and you're getting the same kind of question that appears over and over again. And so this is the kind of question that we would really like to be able to answer. How do you think about transitions of this kind? Okay, so what is the life of a drop? Well, it starts off as a baby. And so this is the drop just after it was put on the bottom of this plate, and it's hanging there. And it looks happy. I can't tell anything about what liquid it is. As with a lot of babies, you can't. They're beautiful, but you can't really tell them apart. The same is true for this. That is, it's just a balance of gravity pulling this thing down and surface tension, which is trying to hold the thing together. And so that determines what the shape is. And so it's a happy childhood. It's only governed by gravity and surface tension. These are the two forces that are important for determining what its shape is going to look like. So then, unfortunately, there's the teenage years. And in the teenage years, that drop begins to elongate. Remember, so it was here, that stubby thing, and then it's going to just get longer and longer. And so you get into the teenage years. And then the question that I have is, okay, suppose I have a cylinder of liquid. Is that cylinder of liquid going to be stable? And of course, you know the answer already. I just told you that surface tension is going to try and bring this into a sphere, right? That's what we said. But I'm not going to allow that one to happen, so I'm going to hold the edges out at that distance. So I'm not going to let the edges come in, so I'm going to keep it as a cylinder. And then I'm going to ask, is that cylinder now stable? And you can answer that question by a relatively simple calculation of just saying, okay, I've got to have the same amount of volume of liquid in this cylinder, but I'm going to let it squeeze down a little bit in the center and get a little wider at the edges so that I keep the volume fixed. And I ask, which of these two has the larger surface area? The one with the largest surface area costs more energy and will flow to the one with the smaller surface area. And the answer is that if this is long enough, then that is longer than the circumference of this cylinder, then this will be unstable and it's going to flow to this because this has a smaller surface area than this one. And once that starts to flow, well, then the neck in the middle here is getting thinner, so there's even more pressure on that point just because of what I just told you before. So this thing is a runaway process, and this thing is going to try to break apart. So the cylinder is unstable, and this is one of the classic instabilities that you see in fluid mechanics called the Rayleigh plateau instability in this case. Now, you've seen the Rayleigh plateau instability before, and you can see it if you just take your fingers, stick them in your mouth, get some spit on it, and okay, so you're all very shy, and you're not going to do this in public. So what I ask you to do is tonight, when you're through with this lecture, go home, go to your bathroom, lock the door so no one can come in. And when no one can come in, then, and no one's looking, stick your fingers in your mouth and spread your fingers apart a little bit, and you'll see a little cylinder of liquid between your thumb and forefinger, and this is going to then start as a cylinder and then going to break up into a little blobby bit in the middle. Okay, so it's something that you can see. It's not something so esoteric. And so I suspected that you wouldn't be willing to show this, to do this in public. So I have a picture of what you would have seen, and so this is the picture. So this is a spider. It's not an ordinary spider, it's what's called a bolus spider. And so this spider doesn't build a web. What it does is it secretes its spidery stuff, and which is hanging from this leg, and a fly comes around, and it does something like that, and it catches a fly, and then it does stuff that spiders do to flies, which we don't care about here. But the reason I got to tell you that story was because you get to see what this long filament of liquid is like. It's not smooth. It's full of this blobbiness. And that blobbiness is just that Rayleigh plateau instability I told you about on that last slide. If you have a regular spider's web in the spring or summer, now you go out in the morning and there's some dew on it, you will see it's all decorated with nice little droplets of water. That's, again, the Rayleigh plateau instability as that liquid that was all along the cylinder breaks up into little droplets. So this is the beginning of how that drop breaks apart. But then, after the teenage years, you get to the midlife crisis, okay? And so the midlife crisis is where this drop is going to break apart, and it's going to have to decide what it's going to do. So I've shown here a picture of just the region of that drop where it's breaking apart. So you can see this is the circular region, and this is that conical section coming into it. And so that's what's happening here on the left. On the right, I have another picture of it, and again, I've cut off the same area so you can just see the cone and the sphere down below. And what I'm hoping you will say is that, gee, they look the same. Why am I showing you two things of the same thing? But what I want to now do is I want to uncover them a little bit so you can see what these were a microscopic image of. And so in the next slide, I've uncovered it, so you can see, I'm uncovering it a little bit so you can see what these things were. So these are the areas that you saw, and then this is what was behind that I've covered up, and now I finish uncovering it. And this is what those pictures were. So I showed you this region here, which is the ordinary drop pointing down, and the drop is falling. And this was another picture of that drop a little bit later, but now I turned it upside down so that the real image was this. Okay, and so what you're seeing is that in this case, I have the break-off event looks identical to that break-off event, but something very different has happened in the physics. In the one case over here, gravity, the thing that's pulling on it, is pointing down. And in the case over here, gravity is still pointing down, but the cone now is pointing up. So these things have the same universal shape at the point of breakoff, irrespective of which direction gravity was pointing. It doesn't matter how this thing was broken off. At the end, the material takes over, and there's only one kind of singularity that it will support. So whether you're taking the, this from the drops coming from your faucet in your kitchen sink, or spray coming off the ocean, if you looked at how that water was breaking apart, in each case, you would see the same structure just at that point of breakup. So what this should indicate to you is, okay, something perhaps slightly universal is going on here. That is, something didn't depend on one of what you would think is the major inputs of the problem. That is, the gravity, the forcing on this whole problem dropped out. At the end of the day, that didn't matter. So now I just want to show you what this thing looks like in a movie, so you can see this thing in real time. So there are just two things I should tell you about this movie. One is that it's our 125th anniversary of Chicago, so our labs are very old. And they were so old in this lab that gravity is pointing to your right, okay? The reason for that is I wanted the long aspect ratio, so we turned our cameras sideways. So gravity is indeed pointing in that direction. And the other thing is that it was taken with a movie that takes 10,000 frames a second, and I'm playing it back at 30 frames a second, so it's a slow motion movie. So this is what it looks like. So this is water. It's being pushed in this direction. This is about 1.5 centimeters up here. You can see this thing being pulled down, and you'll see this neck elongating, and just about now you will see the cone there. And I mean, I don't know about you, but I think it's a privilege just to be able to go into the lab every day and see something this beautiful going on in front of your eyes, right? I mean, it's just something that's stunning to me, the way this thing manages to create that structure in such an elegant and reproducible fashion. And so, I mean, much as I've been trying to tell you why the importance of this research, intellectual importance, I also think it's not amiss to tell you I also do it because I just think it's a lovely thing. And I would not want to miss the opportunity to do this.
Can we see it again?
Oh, thank you for you, anything. Okay, so here it comes. Okay, so that's how this water drop breaks apart. Paul?
There are many different types of singularities. You mentioned conical singularity, but there is also cusp.
Yeah, okay, so we will see a few other things in the next slide. So I'll just show you some other things that you could get in this. So for water, this is what we get, and I think it's right here. So this is basically a conical thing going into a slightly dimpled sphere. So it comes in like this and then comes out. So that's the shape of what happened at right at that point there. But as I think part of what Paul is saying is, well, that's not the only singularity you have. You can tune, as an experimentalist, I get to vary things so I can try to see what other singularities I would get to visit. And there are many of them. Yeah, the angle is reproducible.
The same for low, and upside down?
Yeah, so all of that was reproducible. So that angle was fixed in this, and it doesn't, as far as we can tell, depend much or at all on the viscosity of the thing, as long as I'm in that regime of the physics. But what I want to show you is that I can move from one singularity type to another. So this was what I've showed you before, water falling into air. This is something a little bit different. This is kind of water. So it's water made about 100 times more viscous by mixing in a chemical called glycerol. So it's basically like water, just more viscous. So viscous, for those of you who don't know, so water is low viscosity. You can run your finger through it easily. Honey, where you have to push harder, has a much higher viscosity. So that's what we're doing. We're just changing the viscosity. And now you see that this has a entirely different shape. I have that long, long, thin neck. And then that neck goes unstable and makes a thinner thread. And what I don't show you here is that if I had taken an image just slightly later than that, ever so slightly later, that thin thread goes unstable and forms an even thinner thread. Which if I took, and that's as far as we could do it experimentally, but then you do it on a computer and you can see it goes on and on and on infinitum. That is, you can have the thread forming region to where you end up. This is that pure glycerol on the inside, but now falling into a liquid of oil of comparable viscosity. And so this looks a little different from that. There you have a cone at the top whose angle does change as I change the various compositions of this, but it's still a cone pointing into another cone. And as I change the ratio of the inside to the outside viscosities, then it's those angles that change, Paul. Okay, so again, it's a third type of behavior. Fourth, this is, I have to say, one of my favorite in that this is just pure water falling into very, very viscous outer fluid. And I don't know if those of you in the back can see, but they're still connected by a very thin thread. Those in the front row, I hope you can see that thin thread is still connecting those two things. And why nature decides that's the way it wants to break off a drop is, I think, an astounding thing. So what did I get to do? As an experimentalist, I got to vary a few things to tune myself into each of these different regimes. So I got to tune the viscosity of the inner fluid. That is it water or is it that glycerol? I could do the opposite, the outer viscosity. Is it air or is it a highly viscous silicone oil? I can vary the densities of the inner and outer fluid. I can vary the surface tension between the two, and I can vary the nozzle diameter. And so these are the various things that as an experimentalist I get to tune so that I can move the phenomena that I'm interested in into the window that I get to study. And so that's how I can get to the precise point of being able to say, these are the epitome of what's happening in each of those universality classes. So now what I want to ask is, how should I think about shapes? And so there's, so this is one thing that, idea which I'm going to have to struggle to try and express it properly, and I hope I can get it across. And this has to do with what's called scale invariance. And so remember what I told you about that drop breaking off. As it breaks off, that neck is getting smaller and smaller and smaller. It's getting smaller than any other length scale in the problem. I'm not thinking about atoms at this point, but as far as the continuum limit of a fluid, it's getting smaller than anything else I could define about that fluid. So that's just shrinking away to nothing. It's getting smaller than anything else I could define. Well, if it's getting smaller than any of those other length scales, then the assumption is, well, then the flow in that region can no longer depend on any of those other length scales. So that's what the idea is. Now, you might ask, why would you come up with an idea like that? So let me try to give you some feeling for where that would come from. So suppose you have rain, and it collects on a mountainside, and on the mountainside the rain falls off and flows into rivers, and these mighty rivers go across the continent, and they finally end up in the delta of the river, and the delta breaks that big river up into smaller rivers, brooks, rivulets, and finally that water flows between two tiny little pebbles in the stream. My question for you is, does the flow between those two tiny pebbles depend on the fact that this water originally came from the mountainside? No, it doesn't. That doesn't make sense, right? Why should it depend on what happened all that time ago? It only depends on just that distance between those two little pebbles. That's the only scale that matters anymore because the others have been lost. So that's the idea. That's why you might think that if this scale is decreasing to 0 and smaller than anything else, I can forget all of those other scales. So that's the idea. That's why this is the assumption. And then, so the flow in that region depends only on that shrinking radius. But what does that shrinking radius depend on? On the flow, which depends on the radius, which depends on the flow, which depends on the radius, flow, radius, flow, radius, flow, radius, flow, radius, flow, radius. So what I've written for you here is a fractal sentence. I take any part of this sentence and I blow it back up and I get the original sentence back. And this is a mimic of what the mathematics is doing in this case. That is, what you're thinking is that the solution to this problem is also have this self-similar structure. So the idea is if it depends only on that self-similar structure, then this is why you can begin to think that you will get universal shapes for these problems. And you may be able to get from one regime to another regime, but within that regime, all those shapes should just depend on a few numbers, and these are the few numbers that we get to look at. So what do we mean by that? So here is the picture of that drop. This is the cartoon of the sides coming down. Z is the axial coordinate. H is the radial coordinate from the center to the radius of that drop. And what this mathematics is telling me to do is if I have the solution at one point in time, I can get closer by multiplying this dimension by some number. At the same time, I multiply this dimension by perhaps another number. And so I do that over and over again. And each time I get to have that same structure, just pulled and pulled in these two directions over and over again. And so this is what this drop is supposed to look like at the singularity. It has a scaling structure. And I show data here. I have to show data because I'm an experimentalist. I mean, I don't want you to go away from this lecture thinking, oh, all we do is take pretty pictures. I mean, I don't want to go through what this data is, but the point is that this data is the corroborating evidence for that picture that I just told you. And it's not just pretty pictures, it's actually analyzing carefully what those pretty pictures are telling us. And so this is what emphasizes what's universal in these problems. So that seems to be the end of that story. But now let's just take a look at this. Let me do one more thing. Proverbial one step too far. So you remember this picture, right? This is what I've shown you over and over again. This is the water drop falling in air. Suppose I did exactly the opposite. What would that be? Well, that would be an air drop rising in water. That is a bubble breaking apart. And so if I do one, I can do the other. And you might think that I'm going to get the same phenomena in both cases. So here we're going to see that. So this is an air bubble. It's lit from behind. That's why you have these white parts here. So that's not something inside the bubble. It's just that's acting a bit as a lens. So that's what you're seeing, this white part here. And now we're going to watch this movie. It was a very carefully done movie where it was very carefully leveled, very circular. And then we watch what this thing looks like. And now you can see it start to rise. It's the air bubble going up. It shrinks. You can see the little bit go through the center. It's again something quite lovely to look at. But you may wonder, why did I make such a big fuss about it being very carefully leveled and very circular in all of this? Because I didn't mention that on any of the other ones. Well, the reason is that in this case, it matters. And it matters a great deal, so that what we're saying here is if we took this air bubble and now try to look at it a little bit more carefully and push it a little bit, we see it loses all of that symmetry. So here is, we've let this air come out from a slot nozzle. We gave it a pulse of air, and it flows up. We're just looking at the thinnest part of that air bubble here, and we can see what happens. And so that's what this thing looks like. It doesn't look at all like that nice, smooth, simple collapse that we saw before. So if I do this again, so I stop it there, you can see this is nothing like what we saw before. It looks, if anything, like this sheet of what was torn apart from both sides. But I remind you, what's being torn apart is air and water. I mean, there are no things that are less likely to, you would think, should be described by tearing phenomena, but yet that's what this thing looks like. So what this is saying, and again, with one other piece of data that says, okay, in this case, that whole idea of these universality classes, they're still universal regimes, but in this universal regime, I don't get to neglect those initial conditions. So that whole business about water coming off a mountainside, well, sometimes it cares that it came from the mountainside, and that's what this data is showing here. Okay? So let me finish up this aspect of the lecture on the breakup events in just saying, well, this is a life story of a drop, and as in all life stories, we are always interested in what is nature and what is nurture. So how much of this is intrinsic in the material itself that doesn't depend on how it was treated? And the first part I told you about was all nature. That is, it didn't matter how I dropped the water into the air. It always ended up at that same singularity with that same shape, and I always got that same cone pointing into the sphere. That is, I had no choice about that, no matter how I did it. On the other hand, when I reversed the process, it was nature that lost out, and nurture took over. That is, it depended on how I treated it. And in that case, it remembers nearly everything about how it was started out. And so this shows a bit of the richness of the phenomena. I mean, we thought we had this whole thing licked when we had the first aspect of this done. And then, of course, we did this one experiment too much, and we realized that nature has a lot more interesting things in store for us if we really take this thing seriously and look at all aspects of the problem. So this is where I want to stop with this aspect of it. Now, I just want to continue is that you're in a midlife crisis, and what happens after that? Well, after a midlife crisis, you're in free fall. Right? And so, what's going to happen now? And so, And so what happens to a drop after it's in free fall? Well, it splats, right? And so here is the drop falls onto a smooth, dry microscope slide, and it splashes. And so the question is there anything interesting about this aspect of the life of a drop? And so this is what I want to go on with now. And so I'm going to show you a movie of a drop splashing. This is a drop which is about 3.5 millimeters in diameter, so pretty small. It's made of alcohol, so it's an ordinary liquid. The white spot in the middle, again, is just the optics from the back, so there's no hole in the drop. It's just an ordinary drop of fluid. It's going to fall from about this height, and so it's going to hit a smooth, dry glass microscope slide here at a few meters per second. Nothing fancy about this. And as it falls, you're going to see its reflection in the glass, and you'll see the whole thing. So let's see what this looks like. Here it comes. Okay, so again, it's one of these phenomena which I just really love to watch. And even without your asking me to do it, I'm going to play it again. Okay, so let's see it happen. So it's going to come down. As it hits, you see it generates that corona that goes out, and then that corona then breaks up into all these tiny little drops. So that's the phenomena of splashing. Now, what causes splashing? Well, I know that if I took the velocity at which it falls should matter, the size of the drop should matter, because if I took a tiny little drop and laid it very carefully onto a table, it wouldn't splash. So I know the size matters and the velocity matters. I know that thing I told you about surface tension that's trying to hold it together, that should matter, because if there's no surface tension, it wouldn't hold together at all. Also, the viscosity of the liquid should make a difference, because how easy is this thing to flow? So those things matter. After that, I've said everything there is to say about the liquid, and now I have the substrate. So the substrate, is it soft or is it hard? Is it smooth or is it rough? Is it dry or is it wet? Those are about the things that I can tell you about the substrate. So those are the things that should matter for this thing to splash. Now, one thing I didn't mention was the air around it, because, well, air can't matter, right? I don't feel the air as I do this. It's 1,000 times less dense than the liquid or the substrate. How can the air make any difference whatsoever? However, you know that if you take your hand and you stick it out of the window of a moving car, you feel drag on your hand. Your hand is pushed backwards. So you would think that these small drops that are trying to move rapidly in air are really being impeded. And so if you took the air out, we could get a really important splash. I mean, not this little thing that we saw here, but a much more impressive splash. So let's see that, what happens. So for the third time, you're going to see the movie on the left. So it's the same thing that you saw before. It's a drop in atmospheric pressure coming down, hits, forms a corona, spreads out, and breaks apart. So that should be in your mind as what an ordinary splash looks like. Now I'm going to do exactly the same experiment. It's the same alcohol, the same diameter, falling from the same height onto the same smooth, dry glass microscope slides. The only thing that's different is that I have it in a container now where I've taken out some of the air. So this is 1/3 of atmospheric pressure in here, not much. It's the pressure that you would get at the top of Mount Everest if you were there. So you could live in this atmosphere. You might not be happy, but you could live there. Okay? So everything else is identically the same. So now I want to see this enormous splash coming. So be careful. Here comes a big splash. Watch it. So in the words of Arabi, who ordered that? Right? This was something that just took us totally by surprise. We started laughing hysterically. It took about a month for us to decide to stop laughing and say, okay, we have to start trying to understand this. And we still don't understand all the things that go on here. But it's clearly an important effect. It's the air that, it's not just, and I should just point out, look, people have been studying splashing for 100 years, and no one thought to take the air out because it's a stupid experiment. I mean, the air shouldn't have mattered for all the reasons I told you. That is, it's too low density, it gets out of the way, the viscosity is so much smaller than it, so that there's no way that the air should have made any difference in here. Yet, when you do the experiment, you see it's the control parameter. So, let's see, what you might ask is, okay, suppose I wanted to get the thing to splash again. So if I stopped splashing, so if I just drop it from a higher height, then this thing will come down with more force and start to splash. And so you would expect that I would have a line that starts up there. So at low pressures, I can get a splash threshold at very high velocities. And then at higher pressures, room temperature, atmospheric pressure, then I have to go to very low velocities in order to get this thing to stop splashing. So that's the idea. But look, even now, this system doesn't have the self-respect, decency to behave properly. Look at this. This is not a mistake. This is not an error. What this is saying is that this thing comes down, turns around, and goes back out. So what that means is if I sit myself here at atmospheric pressure at 35 kilopascal and start at high pressure, high velocity, I'm staying at the fixed pressure, high velocity, it splashes. I lower the velocity, it stops splashing. I lower it some more, it starts splashing again. And then only when I lower it some more again does it stop splashing for good. So this is a very bizarre type of phenomena that's taking place. Is it only for things like water that I just showed, or alcohol? So here is something that's 10 times more viscous than alcohol. Everything else is basically the same here. So let's see what happens here. So I hope you can see that this thing is just spreading out. Nothing much is going to happen, right? So let's just finish this movie up. And I think I misled you again. In this thing now has a very different shape as it breaks apart. That is, it now spread out smoothly for a while, and only later did it start to create that thin sheet, which then broke up. So this is, again, something that's happening in the splashing. You can ask, does air matter? And so here we do it at 1/5 of atmospheric pressure, and we stop all splashing. So splashing, the air pressure really is the control parameter in this problem. And if I lower the air pressure enough, I can completely stop splashing. Okay, so other things. So, what happens if I now make a smooth or rough surface? So I'm going to start off at the top one. This is the kind of thing you've seen before, so we'll just watch this thing splash. It's the same, it's a different angle, but you can see that it forms that thin sheet, and that thin sheet breaks up. Now I'm going to look at this one down here, which is a very rough surface. So we just took the surface and stuck it into hydrofluoric acid to roughen it up, and see that you get a different kind of splash. That is, as this thing moves out, it breaks up into all sorts of bits. And now, what happens if you go in between those two cases? So I should get some kind of weird splash. Well, what is the weirdness that you see? It stops splashing completely. So again, phenomena after phenomena is just mind-boggling. What is nature trying to prove? Okay, so I probably am running a little late here. So I'm going to just say what the question is that we were asking here. So what we wanted to do was we wanted to find out, okay, so if air matters, where does it matter? And so does it matter below the drop? That is, as it's coming down, it's catching air below it, and is it that air which is somehow changing its behavior? And these things I'm not going to show you here now is we were able to do various kinds of imaging to be able to see, no, the air underneath the drop is not doing anything serious to this. So that's the part I'm skipping now. I'm not going to try and demonstrate that to you, but that's what these experiments were all about. We can do that. But now what I want to ask, so where else could you look for the air? And so another place that you could look for the air is on top of the drop. That is, if it's not below it, then there's on top and at the sides, right? So the next thing, so how are we going to be able to see what's happening to the air above this drop? So this is what I'm going to show you here. So this is the drop shown using what's called Schlieren imaging, which is a type of optics that tries to get you to see much more clearly small index of refraction changes in the air, in the index of refraction of the air. So again, you can see this on a hot day if you're at the airport and you see the heat rising from the pavement and it wiggles and shimmers. We're just trying to take that aspect of the air movement and magnify it because of the small index of refraction changes. And so that's what we're doing. So this is what we've done here. And so I'm going to show you this. I'm going to stop this midway so you can see what to look for. So this black region here, that's just a slide. That's the uninteresting part. That black thing at the top, that's just the drop. And in this case, the drop is not the interesting part. I don't want you to be paying attention to the drop. What I want you to be looking at is all the subtle changes in the grayscale of that region in between. So here it stops, and I stop it here. And so this is what I hope you're looking at. So you see that the drop is completely black uninteresting. But you see that you can now make out the wake behind it. You can see those two gray lines coming up from the sides of the drop. That's what I want you to be paying attention to. It's those gray scales which are what I want you to be looking at. And now I'm going to play the whole movie for you, now that you know which part to look for. Okay, so here it goes. Here it comes down. Okay, so there's a beautiful amount of physics happening in the air above the drop. It wasn't just the drop itself, which has all this beautiful physics associated with it, but you can actually image the air. And what you saw was the air going out and curling up into a vortex loop around the edges, which is what this kind of photography was able to capture for you. Unfortunately, what these experiments also showed was that it's not the air above the drop that is creating the splash. So that only leaves the air at the edges. But this is the kind of experiment that's able to show that and demonstrate that aspect to you. So this is kind of the end of the story of the life of a drop. I mean, there are other things we could talk about, but this is where I think I'm going to end tonight. That, I've tried to show you different aspects of the life story. And I hope that you kind of felt the same way I do. I mean, at least this is what I'm hoping for, is that it's supposed to arouse astonishment in you that, wow, is this what a drop is doing? So next time you're kept awake at night because your tap in your bathroom is going plop, 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 and driving you nuts, you can kind of calm yourself down by saying, oh, there's beautiful phenomena with each time it breaks off, and beautiful phenomena for every time it splashes. And the air itself has a beautiful phenomena that's engaging with the liquid. So nature is subtle. All of these things were not obvious. None of this stuff was obvious to me. But one of the things that I like about it is that we seem to have the tools to begin to decipher the physics that's going on here. And that I didn't talk too much about how we think about this, but similar concepts are used in all of the ways we address this. So the things that I'm particularly talking about now is the idea of scaling. I mean, these ideas of scaling and the criticality of going to a singularity and how we treat those singularities. Those are what's happening over and over again. And this puts me in mind of the quote by the philosopher of science Alfred North Whitehead, who said a great idea, and this I'm thinking about all of the work that's been done on scaling over the past 50 years. A great idea is like a phantom ocean beating upon the shores of human life in successive waves of specialization. And I think that somehow captures something about how we've been able to attack this problem and many others like it using the same set of ideas, but each time the ideas come back in a slightly altered form with slightly different ramifications for the subject at hand. Okay, and with that, I want to thank you, and these are the people who did all the work, and I've tried to give their pictures as we went along, but these are the people. Thank you very much.
Happy to answer questions?
Sure.
Questions, comments?
Can I ask, Sidney, about some of the stuff you didn't show? Your beautiful pictures of the drop showed what you see if you look at the drop from the outside and you see its shape. Essentially, you're seeing a boundary between the drop and the medium that it's in. Can you get any information about what's happening inside the drop? In other words, is there a pressure wave? Is there a variation of pressure? When we know that liquids are, like water, is essentially incompressible, so that if you make a tiny change in volume, you get a massive change in pressure. Can we see the internal dynamics of the drop in any way?
We haven't been able to do that. I mean, there are probably some things you might be able to do, but you really, they'd be hard because remember we're doing this at 50,000 frames a second in some of these things, so we don't have a whole lot of either resolution or time to look at it. But so where you see that is when you do various simulations of this. These now become the benchmark for which we heard about all sorts of computations that you can do earlier today. I mean, so in order to do this, you really need the benchmark to be able to compare to see what's going on. And so a lot of that work has been going on to try to do these kinds of simulations. But there are techniques you could try. You could try putting some fluorescent dyes in here and watching how those might flow around. You can try and put tiny little particles in and try and watch, can you do PIV and watch them move around. Those are pretty difficult to do. So that's for the next generation.
Wouldn't changes in pressure show up under polarized light coming through?
Well, not for water. I mean, you could do that if you had a polymeric fluid or a liquid crystal fluid dropping, which we've done a little bit of that, and you can see certain patterns with cross polarizers, but not with water. Is just isotropic, so you're not going to be able to see much.
Is the temperature a factor for the experiment?
I'm sorry?
The temperature of the liquid or the air? The temperature in...
Oh, no, okay, so no, the temperature is not important. That is, so we've done all of these things, fixing the temperature, but, and then you can also try to estimate something which we were worried about at one point, which was, okay, so this thing is breaking apart. Does the mechanics of breaking apart heat this liquid up to some extent? And so when we did the calculations, it was around 1/10 of a degree. So really irrelevant to anything having to do with what's going on here. So we don't think the temperature has anything to do with it. We can do the same experiments at different temperatures and check that that's not what's happening. The other thing is, how about the, what is the pressure? Are we sure it's the pressure and not something else? And so you can backfill with the same fluid that you're dropping, so that the vapor it's its own vapor pressure rather than some other vapor pressure. So you can do various checks like that to make sure that the story I told you is about the same. Pardon?
Because it's small scale. I mean, if this is something as big as
Yeah, but remember that at the point of this breaking apart, it's always going down to that small scale. So that's...
Have you studied drops dropping into water? I just remember my cup of tea when I pour the milk and I have a little drop jumping out of the water.
Yeah, I mean, so that's another whole thing. That's better understood phenomena because there, you know that the drop that's going down is penetrating into the liquid. It leaves a cylinder of hole behind it. Then that cylinder of hole, much like the air bubble, starts to collapse. And that collapse is very rapid, and that shoots out a thin jet in back of it. And so that's a different kind of phenomenon. So all of this, just to be clear, was all on dry substrates, not on wet. And when you get on the very famous pictures of Harold Edgerton of drops into milk, we're always into a thin layer of milk. And so he adjusted it to be just the right thickness so you get the most symmetric behavior. But again, that's again into a wet substrate, not into a dry.
There's a question.
That one you showed about the pressure, I guess there is quite useful vehicle. There's implications because people are trying to study altitude sickness and that. The way the drop breaks up might make a big difference in some lungs, the liquid and the air being breathed in. Medical people might be interested to see that.
That never occurred to me. That's interesting. I mean, I don't. I have no idea, but that's certainly a possibility. I mean, the other place that I guess it's kind of important is for NASA. When you go out to the moon, this is going to say that you don't get any splashing on the moon. There's no atmosphere. There's no splashing. But you might, on Mars, see a little bit of splashing, because there's a little bit of atmosphere. So, that's the other place you might look for.
Sidney, very nice talk, and it looks like very rich physics. Actually, not a question. I'm thinking, in one you mentioned about singularity. So, the black hole of the singularity is very hard to do the experimental. And there's no object. So I see that point, the singularity. Do you think the able to simulate some kind of black hole?
Look, I mean, I've read enough popular literature about black holes to know there's a singularity, but I haven't read any, I don't know enough about the real physics of the black hole to know whether I can make any analogy between this and there. Certainly, some of the words are the same, but this is really, I'm following the dynamics view here, and I know something about how the two sides of the singularity are connected. I don't know anything about that for the black hole. So I would say it's a great question. I'm just not. Oh, well, there is one thing. There's been a lot of work by, what was his name? Pretorius, I think, from Princeton, who was looking at black hole coalescence in 5 dimensions and got lots of beautiful structures out that are very reminiscent of drop breaking up, but reminiscent but different. So there was some relationship there. But
yeah, I heard someone using the fluids, the vortex, to simulate the black hole. But the velocity is a problem because if the velocity is too high, they have a shock. And this one is very steady. So you see the similarity, but the fluid speed is very slow. So it's very nice.
It's kind of had a little silliness in my mind. Goes there sometimes. So you have the drop going on in the gravity. If you say, for instance, it's coming through a stall and you reverse it, does it reform in the same reverse image or?
Yeah, so you have to be careful about that. So there are certain things, yes and no, it depends on exactly what you mean by that. So there are substrates that you can make that are so almost perfectly hydrophobic, as they don't like liquid on them at all. And you have a drop, if it's not from too high, it comes down, it spreads out, and then it comes back together and bounces right back off of the substrate. That is, it can do that. So that's a bit like what you're asking. But that's under that particular type of geometry. If you, another thing that you might have been considering is, well, okay, I take a drop and I break it apart and the thing breaks apart. Suppose I bring the two together again. That's a very different problem because the geometry at the beginning of bringing it together is this, and that's a very different geometry than that long thin cylinder that you started. So you have to be careful.
Thinking just at the moment before it breaks apart and you reverse.
You can do some of that. So some of that you can do with very careful engineering. But at some point you're lost because it's gone too far and you can't get it back.
Can you give us some idea of the experiments that you photographed, which were pretty well water falling in air, hitting flat surface, which I guess was our last microscope slide. If you look at the kinetic energy flow, so initially the kinetic energy in the drop is moving down, and afterwards some of it is going out to the sides, a little bit is coming up a splash, and some of it must be going into the recoil of the whole slide being compressed down. What fraction goes into the splash?
Okay, so
And is that understandable?
no, so look, you can. Let me just back up for a second and say, why is this such a fiendishly difficult problem for us? It is because, look, I misled you. I mean, I apologize. You know I did. That is, I told you you weren't going to see it. You were going to see a big splash. You saw nothing. I mean, I knew that was coming. But what I didn't mislead you about was how I was thinking about it when we did the experiment. I mean, this, I'll bring you through the same history that I did in going through that. So, so your question was
Essentially, what fraction?
So what's wrong with this? So this impact is by far the strongest forcing in the whole problem. The spreading out, once it's spreading out, well, the velocity is in that direction. Why should it ever turn up? And so the only reason it can turn up is what I was saying, is it's this air at the edge which is somehow trying to confine it in. And so now this is kind of a third order effect that you're trying to get right to be able to see anything about the splashing. So that's why it's been so difficult. And so I don't think we have any, back of the envelope calculations for how much should come up, but but it's not going to. But you're right. I mean, it's only the stuff that actually breaks off at the end which breaks up, and that's only what's in that corona, and so that's a small part of the whole drop.
It might be caused by boundary effect. So it's like there's a ground effect in the rockets. Yeah.
One last question.
You said that when a drop is on a flat surface, what would happen for it on a sphere or on an edge? What's that you say?
No, it's so we've tried some of these, and we have gotten pretty close to as less progress there than we did on the flat surface. So it's one of the things is that if you do it on the edge, we were trying to see whether we could see how much of this, well, what should I say? You can tilt the slide. So it comes down on a tilted slide. So now you've broken the symmetry of the left, right, and around. And we thought that that was going to then be a nice, simple tool for us to be able to measure the azimuthal direction of this, which is the simplest thing. The sphere is a little hard for me, but I can just tilt this thing. It turns out that it's not just the symmetry is broken, it's not just a simple azimuthal behavior, but it's something how it's catching the air underneath, which is making a difference. So there's a problem with that. So it doesn't go over easily.
The life and death of a drop. As with drops, so with public lectures. Our time is almost up. Let's thank Steve by making a big splash.